Welcome back to my lectures on groups, rings, and fields. Our next topic is free groups. We have learned free abelian groups earlier when we tried to prove the fundamental theorem on finitely generated abelian groups. Free abelian groups are abelian groups generated by a set of linearly independent elements. But free groups are different. It is more generalized form of free abelian groups, and in most of the cases free groups are not even abelian. When the number of generator are more than one, it is no more an abelian group. But still, we have a nice relationship between free abelian groups and free groups in the end of the section. So let us start with free abelian group, just to recap the definition of free abelian groups, so that you know the difference between free abelian groups and free groups. Let's start free abelian groups. Free abelian groups. This we already learned earlier. Okay, a group G, an abelian group G. Group G is a free abelian group. If it is generated by or it is uniquely generated by linearly independent elements. Uniquely generated means an element of G can be uniquely expressed as a linear combination of these elements. Examples are Z cross Z. Generators are 0, 1, 1, 0, 0, 1. Counter examples are Z2 times Z3. This is not free abelian, because though we have a generating set, they are not linearly independent. So this is the idea of free abelian groups. Our new topic is free groups. Free groups. So we want to define what a free group is. So first thing what we are going to do is we are going to define the elements and then operation. Okay. So let A is equal to AI. I belongs to an index set. Be a set. Then we are going to define, this is actually the alphabet of the group. Okay, we'll come to that later, why it is called alphabet. Then we'll define a syllable. Syllable is defined as an object I to the power of ni, where ni are integers, and ni belongs to 0. See, this is not a multiplication of ai ni times. It is not that. It is just an object that we'll write it like this. We can also write ai ni as ai n times. This is also not multiplication. We are placing an ai next to it. It's called writing it in a juxtaposition, or concatenating a and I times. It's not a multiplication at all. We are not considering this as a multiplication because we haven't even defined multiplication. So this is a syllable, and when ni is equal to 0, we write ai to the power of 0 as 1, and that is going to be our identity of the group. Now this is the syllable, and we are going to define one more term called word. A word is a finite sequence of syllables written in juxtaposition. Examples: word w equal to a1 to the power of 7, a2 minus 2, a1 8, a3 6, something like that. Now we are going to define two types of reductions in a word. Two types of operations in a word. It's called reduction. Reduction on words. The way we are going to define reduction is if ai to the power of m and aj to the power of n are adjacent to each other, we can write this as a to the power of mn. That is one reduction. So in case if you have a word like this, a1 to the power of 7, a to the power of minus 2, a to the power of 3, a 3 to the power of 1. This you can write it as a1 7, a2 1, a3 1. That's what this says. We are reducing this word to this. Another reduction is ai to the power of 0 is equal to 1. So these are called elementary reductions. So now we are ready to define a group. Okay, a free group or let us start with defining the group, then we'll come to it as a free group. Define a group as follows. The group contains words. Define a group on a set A. The group contains words. Generated from elements of A. Meaning there is an A here and words are the words are defined like this. And the binary operation of the words W1 and W2 is W1, W2 placed in juxtaposition, meaning they are concatenated. Okay. The reduced binary operation of W1 is the reduced form of W1. Reduced form. By the way, reduced form means a word is reduced if it cannot be reduced further using elementary reductions. Okay. So W1, W2 is the reduced form of W1, W2. So that is how we define this group. This group is called a free group, is the free group on A and is denoted by F. So that is our starting point. That is how we define the free group. We have a couple of variant definition on free groups. So in a different way of telling the same thing. So let G be a group and AI is a subset of G. Then if there exists an isomorphism phi from G to F of A, this is our A, by phi of AI is equal to AI. See, this is just a subset of GI. So we are defining only taking by few elements of G. That means G is generated by AI. Then only this will even become a map. So if there exists such an isomorphism, then we say G is free on A. It's a different way of telling the same thing. FA we defined as the set of words with the operation as juxtaposition of words, and the identity is 1. Here we are defining in a different way, and a group G is said to be free if there exists a set A such that G is free on A. A different way of telling the same thing. Now let us see the properties of, what are the properties of a free group. Properties. The first thing is, a free group is always infinite. Always. Second thing is, if the number of generators are more than 1, then it is always non-abelian. Why? Because if A is equal to, let us say, A comma B, then G contains elements of the form A, B square, A square B, etc. And if you multiply A square B times A square B times A cube B, and that is actually equal to A cube B times A square. That is not equal to A square B, A cube B times A square B. So this definitely is not abelian. So if it is more than 1, but if it is 1, when the number of generators is 1, then the free group is abelian and cyclic and is isomorphic to C, because it has got only one element. It has got only one generator. A is equal to A. So the words are A square, A to the power of minus 1, A to the power of minus 7, A cube, etc. So when you multiply this or placing the juxtaposition, these are the words. These are the syllables. When you create a word, it will be A times A cube times A to the power of minus 7. And that times another A4 times A cube, then the whole thing will become something like this. So this is actually isomorphic to, FA is isomorphic to Z, when A contains only one element. If it is more than one element, this is how it is going to be. See, if you take two words like this is word 1, this is word 2, and this is word 2, and this is word 1. So this is not commutative, and then and hence the free group here is not abelian. more properties. A group G, if a group G is free on A and B, then the cardinality of A is equal to the cardinality of B. This is a very simple property of free groups, because G is free on A and B implies there exists isomorphism phi from G to Fa and psi from G to Fb, and that implies there exists a isomorphism from what is that? We'll take a psi inverse of F phi is from f of b to f of a is an isomorphism, and that implies b is isomorphic to a, and that implies a is equal to. So that means doesn't matter which doesn't matter the set of generators, if a group is generated by any of such generators, their cardinality is same, and that actually calls for a definition. It's called rank. It actually coincides with our rank on free abelian groups. So the number of elements in a number of generators of a free group is a constant and is called the rank of G. Suppose, for example, if G is generated by f of a comma b, then the rank of G is equal to. And this also implies if two free groups are isomorphic, they have same rank. Another very easy property is any non-trivial subgroup of a free group is free. And that is because if G is equal to f of A and H is a subgroup of G, then H is actually generated from a subset of A. If it is A, then H and G are equal. This implies H is generated by a non-empty subset of A, and that implies H is free. If you take the same set A, then H and G will be equal. So it has to be generated by a subset of A, meaning it is again a free group if it is non-empty. Now let us do a very simple result on homomorphisms of free groups. So, theorem, let G be generated by A is equal to AI, I belongs to some index set, and G prime be any group, and then there exists at most one homomorphism phi from G to G prime such that phi of AI is equal to AI prime, where AI prime belongs to G prime, not necessarily distinct. These are not necessarily distinct. See, here we are not saying that G is a free group. Okay, one more part for this theorem is, and if G is free on A, then there exists exactly one homomorphism. Sorry, homomorphism, yeah. This is, see, the first statement, it is not saying that G is a free group. It only says that it is generated by A. Not even saying that it is a abelian group, it's uniquely generated, nothing like that. So, for example, G could be something like Z2 times Z, which is not even a free abelian group. So, in this case, this is not, there is no homomorphism like this, because this is generated by 1 0 and 0 1, and when you express the elements from here, it is not uniquely generated. Okay, so it is not even a map if it is like that. So that is what I am saying. Say when it is free on A, then there exists only one. There exists exactly one homomorphism like this. So since G is generated, that's a proof. Generated by A is equal to AI, I belongs to I. Every X belongs to G, X is equal to pi, I is equal to 1 to n for some n, AI to the power of ni. But this is not uniquely determined, okay? This is one of the representation of X. So, any element can be written like this. So assume that there exists a homomorphism. If there is no homomorphism existing, there is nothing to prove in the first part. Okay? Suppose there is a homomorphism. Suppose there exists a homomorphism from phi g g to g prime by phi of ai is equal to ai prime, then phi of x is equal to phi of pi I to n ai ni, and that is equal to, because it's a homomorphism, pi of 1 to n phi of ai ni, and that is equal to pi of I 1 to 1 ai prime is well defined because the values of the homomorphism is determined by its value on the generators. What it says is, if there exists a homomorphism, here there is no homomorphism that exists. If there exists a homomorphism, then this is true. And that implies there exists at most one homomorphism from G to G prime. Because this is well defined, so there is only one homomorphism defined like this. Now, let G is free on A implies x belongs to G implies x is equal to pi I is equal to 1 to n ai ni. Here ai's are not necessarily distinct because it can repeat, and that implies phi of x is equal to pi I is equal to 1 to n phi of ai ni, and that is equal to pi I is equal to 1 and ai prime, which is well defined. This is exactly like here. So there exists a homomorphism when G is free. That is because every element of G is uniquely expressed in terms of elements from A. If it is not uniquely expressed, then you don't have a homomorphism. If it is uniquely expressed, there is exactly one such homomorphism, because the values of the homomorphism is determined by the values of the homomorphism on the generators. Now let us do a corollary of this theorem. Every group G prime is a homomorphic image of a free group. G. So it's very simple proof. Let G is equal to AI prime, G prime is equal to A prime, where I belongs to I. And let A is equal to AI belongs to G with the same number of elements of G prime. Meaning it could be repeated. AI could be repeated, okay? This is a group and this could be repeating, not necessarily distinct. This implies the cardinality of A is equal to the order of G. Now, then using the previous theorem, there exists a homomorphism from there exists a homomorphism phi from f of A, and this is our G, to G prime, defined by phi of AI is equal to AIJ, A prime, AI prime. These are all elements from here. So this, because of this implies that okay, this is actually the cardinality of A is equal to cardinality of G prime, sorry. Okay, this implies that phi is onto homomorphism. And that implies phi of G is equal to G prime. And that implies G prime is a homomorphic image of G that is equal to f of a free group. Now we are going to take a look at the relationship between free groups and free abelian groups. So let G be a free group. That is, G is equal to f of A for some A is a subset of G. Now, consider the commutator subgroup C of G. What is the commutator subgroup? C is equal to it is generated by or the smallest subgroup containing the set of all A, B, A inverse, B inverse, A comma B belongs to G. This is called, this is a commutator. And this is a commutator, this is a set of commutators So this is the subgroup generated by these commutators, meaning the smallest subgroup containing these commutators is the commutator group, subgroup of G, and C is normal, and G over C, the factor group, is abelian. We already established this when we did the factor groups. Now our claim is G over C is a free abelian group. So we are starting with G, which is just a free group, and we took the quotient of this free group over the commutator subgroup. How do you prove this is a free abelian group? It's already an abelian. All we need to do that it is generated by a linearly independent set. Okay. So for each A belongs to A, the set AC, A belongs to A, is the generating set, of G over C. See, any element of G over C is of the form A, C. It's a coset, left coset or right coset of C. And these are different elements from A. So definitely AC is not equal to BC whenever A is different from B. Okay? And see this clearly, every element of G over C can be written as a linear combination of elements from AC, A belongs to A. And since AC is not equal to BC, implies A is different from B, they are linearly independent. And that implies, and it is also uniquely generated. So that implies G over C is a free abelian group. And this is the relation between free group and free abelian group. A free abelian group can be expressed as a quotient group of a free group over its commutator subgroup.